We're going to start with the infamous question 120 and how to work on that one, and then we'll do some new stuff that you guys can get some practice on, and you can see how I take care of that, how I take care of some new questions. All right, so I think the reason why 255, I think the reason why 120 was giving people so many problems was because, to be honest, I don't think it was anything different than what we did in the book, except it had one step in it that required you to think a little bit outside the box, and I'll show you what I'm talking about. So let me, you know what? Let me just give me 1 second. I have to grab from my printer. I made a scan of my work. I'm just going to grab that scan. Just give me 1 second. I'll be right back. Okay, yeah, sorry about that. I have the I just had to get my work for it. Okay, so let's take a look at the actual question and see what's going on with it. So it says you perform a combustion analysis on 255 milligrams of a substance that contains CH and O. So that's a pretty standard setup for a combustion analysis question. And it says you find that 561 mgs of CO2 is produced, along with 306 mgs of the H2O. Determine the empirical formula, and then we'll go on to the next step, which is determine the molecular formula. All right, so hopefully you guys who are doing this were able to get a start. So I mean, the two things that you can get right away are the CO2 and the H2 and the H, and we can get the H from the H2O. So in essence, what we're doing is we're taking CxHyOz, we're burning it with some oxygen. We're making carbon dioxide, and we're making water. And, you know, from the carbon dioxide and from the water, we can go back and we can figure out, well, how much carbon was in this guy and how much hydrogen was in this guy. And the problem is with the oxygen, we can't figure out how much oxygen was in there from the carbon dioxide and the water, because we also have another source of oxygen, which is the O2. So some of the oxygen in the CO2 and some of the oxygen in the H2O is going to be from a mixed bag. It's going to come from both the organic compound that we're interested in, plus the oxygen that was in the air. All right, so let's work on the carbon dioxide and the water first, which is probably pretty straightforward. So the carbon dioxide is 561 milligrams. So we're going to go through our standard line to start working with this. We got to figure out basically how many mgs of carbon were in there. And it doesn't necessarily have to be milligrams. It could be grams if you want to go to grams. Doesn't really make a difference, but I'm going to go to milligrams just to do something similar to what I did in the video. So we got to get from the milligrams of the CO2 to the milligrams of carbon. We have to go through the number of moles of carbon dioxide and then figure out how many moles of carbon were built into that. So we put our 1,000 milligrams for every 1 gram. That gets us to grams. And then we have our 44.01 grams of the CO2 for every 1 mole of CO2. And then for every 1 mole of CO2, we have 1 mole of carbon. And then for the mass of carbon, for every 1 mole of carbon, we have 12.01 grams. And so that's going to get us the mass of the carbon, and that was 153.1 milligrams.
Dr. K?
Yeah.
Quick question. So, your arrows in this one, like they go from the reactants to the products, so they could go in either direction. They're just like, they're purely to help you understand that like the C in the CO2 goes to the C and the CX, and the H in the H2O goes to the HY, right?
Yeah, well, it's right. So this is not these arrows, the sub arrows down here. These are not denoting any kind of information about the reaction itself, right? What those are denoting is just, it's basically showing you that the hydrogen that's built into the water is coming from the hydrogen that's in that molecule, that substance. And the carbon that's built into the carbon dioxide is coming from that carbon in the substance. So that's all I'm trying to show there. It's not necessarily any kind of indicator that a reaction is going on. We're not taking these out and going back or anything like that. It's just purely to show that this is where those elements are coming from in the product, if that makes sense.
Thank you.
Okay, so we have 100.
I have a quick question.
Go ahead.
Sorry, isn't it 153.1 grams carbon, not milligrams, because we converted from milligrams to grams.
Oh, you're right. I left one last step out at the very end here. Thank you very much. And of course, if we want to get milligrams, for every 1 gram, there's 1,000 milligrams. And then we get the answer that I got, which was 153.1 milligrams. I apologize. I left that one step out. Okay, so at the very end there, yes, in order to get back to milligrams, we have to put the 1,000 milligrams at the very end at the top.
So we're always going to want to convert back to what we started with. So like if the question asks for milligrams, then
just bear with me. Just bear with me for now, and you'll see why. I'll show you'll see why we're doing this. But just kind of bear with me in terms of why I'm going about it doing it this way. You can actually go to grams, and it doesn't really make a difference. But I'll show you in a second why I just elected to do it this particular way. But anyway, so just, you know, you have some options here. I just happen to select this particular option, but, and I'll explain where you can go slightly different and still get the same answer. Now, let's just do the hydrogen real quick. So we have 306 milligrams of H2O. And I'm gonna write the line down kind of quickly because I think we were getting this. In this case, the molecular weight is 18.02 grams for every 1 mole. Now, the major difference here is that for 1 mole of H2O, there are 2 moles of H. And I actually noticed this. A lot of people were sending me 104, and they were telling me in 104 that, you know, in N2, they were saying that 1 mole of N2 is equal to 1 mole of N. And I was like, no, it's equal to 2 moles of N over 1 mole of N2. So that's why a lot of people were getting half for that. So you got to make sure you look at the molecule and see what's in there. So with the water, there are definitely 2 moles of H for every 1 mole of H2O. And then for H, the molecular weight is much smaller. That's 1.008 grams. And then we'll go from grams to milligrams. And so this guy is going to give us 34.2 milligrams. Oops. 34.2 milligrams. Okay, so now we have a bit of a problem, right? This is probably where a lot of people got to, and then they said, "Oh no, what do I do? How do I do this? Where do I go from here?" So what you have to remember is that this sample weighs, I think it said 200, how much did the thing weigh? 255 milligrams. So your sample of CHO is equal to 255 milligrams. So if the whole thing weighs 255 milligrams, then my 255 milligrams is going to equal the carbon plus the hydrogen plus the oxygen, right? So the carbon that's in there plus the hydrogen that's in there plus the oxygen is in there has to add up to get that. Now, the good thing about doing it this way is it's kind of quick, right? Because now it just becomes an addition and subtraction problem. This is conservation of mass. And we're not doing anything with the oxygen that came from the air, right? We're not doing that because we know how much carbon there was, we know how much hydrogen there was, and now we're purely taking our original mass and calculating the oxygen directly. So if you do this, you get 255 megs is equal to 153.1 megs plus 34.2 megs plus X, and you get, for moles of oxygen, you get 67.6, I'm sorry, you get 67.6 milligrams. So the mass of oxygen is equal to 67.6 milligrams. Now, probably at this point, that probably answers most of your questions. I'm guessing that that's where a lot of people kind of got stuck. And if that's not the case, you can type in the chat and just say, no, there was something else that I didn't understand. But I think this is going to get most people over the boundary. Now, where do you go from here is probably the next question. Well, now that we have our 3 masses, we can take our, let's just go back and get them, our 153.1 milligrams. Oops, I'm sorry, guys. So we have our 153.1 milligrams of carbon. We have our 34.2 milligrams of hydrogen. And we have our 67.6 milligrams of oxygen. And we can convert each one of these to moles. Which I guess, you know what, since we're doing it, we'll just do the whole problem. Might as well make sure that everybody's on the same page. So if you want to convert these to moles, then it just becomes, you divide by 1,000 milligrams, and you have 1 gram. You have 1,000 milligrams, and you have 1 gram. That's all the same because we're converting from milligrams to grams. And then you just divide by the molecular weight. So you have 12.01 grams per 1 mole. You have 1.008 grams per 1 mole. And you have 16 grams per 1 mole. And those just come directly from the periodic table. That's nothing, no magic there. All right, and so now you can just get the number of moles. So if I look at my little cheat sheet here, the number of moles of carbon were 0.01275 with a little line under this, moles of carbon. You get 0.03396 moles of hydrogen. And you get 0.00423 moles of oxygen. And then now we go through the steps of determining an empirical formula. So remember, the first step always with determining an empirical formula, no matter what, you got to get to moles of each compound. So that's what we just did here. We did that lengthy process above was designed to get us to moles of each of these elements. And now once you have the moles, it becomes straightforward. You divide by the one that has the smallest number of moles, which in this case is the number of moles of the oxygen. So you take 0.00423 moles of the oxygen. You divide each one by the 0.00423. And then we're going to get our ratios. And the ratios in this case are going to be 3 to 8 to 1. So you get the final empirical formula is C3H8O1, which has an empirical formula weight of 60.094 grams per mole. And the way that I get that empirical formula weight is I take 3 times 12, because there's 3 carbons, 8 times 1.008, there are 8 hydrogens, and I take 1 times 16 because there's 1 oxygen. And so you should come up with an empirical formula weight of 60.094. So if you want to get the molecular formula, that's going to equal the molecular weight divided by the empirical formula weight, which is equal to the 180 divided by the 60.094, which is going to be 3. So you multiply each one of these coefficients by 3, and you get C9H24O3. So those are the answers for the first and the second part.